and this forms the basis of all the deep learning, all the advanced neural network machine learning algorithms that you will either study or through your own, or you will go see in future. What neural is and why do we need it? Okay, so the neural network was initially inspired from how our human brains work. In our brain, we have multiple neurons, a network of neurons in our brain, which passes information to one another. So if you see, say for example, if you see some apple or so, the image that you see through your eye goes through your brain and multiple different neurons are fired. Not all are fired, but only some of the neurons that are fired, and then it actually helps you perceive that what you are seeing is an apple. So, based on this idea, so in your brain you have like these neurons, which are these tiny things that you see are dendrites, and these are the connected to another neuron-like structure. So these dendrites that you see are connected to the neuron that are another neuron. So these are all connected networks inside your brain. So this was the whole idea that in the brain, when you actually see something, there is a network of neurons that are connected, and when you see some of the neurons gets light up, and others are not so lit. And based on this interactions, you are able to perceive the world properly. So let's look into how this has inspired our network. So before we go into the neural network, let's first revisit our linear model first. So a linear model that we have done in the very beginning of the class was that, say for example, you have a data point x and lambda is some weight. So your linear model simply becomes sum over lambda I xi and I. So x is uh, some vector of some instance. So for it's a vector of xi, x1, x2, x3, x4, and lambda is the is the weight. So lambda I times xi, sum over that is a linear model, right? So this you can represent using this kind of a network. So all these neurons all these circles that you see on the left hand side are x's, x1, x2, x3, x4, and all the weights that you see, all the connections that you see are are weighted with lambda 1, lambda 2, lambda 3. So this this diagram simply represents that you take each one x1 times lambda 1 plus x2 times lambda 2 plus x3 times lambda 3 plus dot 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 dot, and then you whatever the value it takes is the sum of all these values. So this neuron represents the sum of all these inputs that you get from these. So this is what the neural linear models were. To train it, you used a least square. The loss function that you used was the L2 loss, or the mean squared error loss. That this is the linear model minus the what is the prediction whole square. It was the loss, and then you calculated what is the actual weight for lambda i's. That's how you did the linear model. But there are problems that you cannot learn a very complex representation. Say if you want to learn a complex representation that given all these x's, x1 to x3, x4, x5, find the largest x in it. You see? So, or maybe the other could be, say, you want to learn an XOR function. So XOR function is a very simple function where you say 1, 1 is 0, 0, 0 is 1. 0, 0 is also 0, 1, 0 is 1, and 0, 1 is 1. XOR function is not a linear function, and no values of lambda I can ever learn a XOR representation. So a linear model is nice. It's actually very easy to learn. It's very easy to define, but it cannot learn a complex functions. So to learn a complex functions, we need to introduce non-linearity in the system. So how the non-linear system looks like? So this is your linear model. So what we can do now to make it non-linear is that we can add a function f on this summation. So now this function f is a non-linear function. You're Now the current with nonlinear score looks like f of summation over lambda I xi, where lambda i's are the weight and f is some function, which we will see in the future that what these functions could be, but it could be any function that of your choice. So this is how you made your function non-linear, and this kind of function can actually learn complicated representations or complicated functions. So now let's neural network is the extension of this basic fundamental idea that you take a summation of xi lambda I and make a nonlinear add a nonlinear function. So this becomes your score, and neural network just builds on this idea. Let's see how they do. So before we define how neural network works, let's first define some of the terminology so that when we talk about neural network or when you hear word neural network, you're able to follow what they are doing. So consider this a neural network where these are all the red circles that you see are called nodes in the network. Just for the sake of understanding what is the background, how many of you are already aware of neural network or have done some course or some idea about neural network? Just raise your hand so that I can see how many of you are aware of. Depending on that, I can increase the pace or decrease the pace. How many of you are already aware of neural networks and how it works and how it functions? Okay, one. So anyone else is aware of? Okay, I see only one hand raised. Anyone else? Okay, so assuming not everyone is familiar. Okay, now you can put down your hand, Kavita. Thank you for sharing. Okay, so then we will just go slowly then. So the neural networks, all the red circles that you see are called the nodes of the neural network. Okay, so whenever you hear nodes or neurons, so they are talking about these circles that you see in these neural network design. We will come to know that what are these nodes and why do we call it nodes and neurons. It's just that the terminology and the definition is such that we will see how they are connected. So these are called nodes or neurons of the neural network, and these are called the red line again are called the connections of the neural network. That this node is connected to this node via this connection. The red line that you see here is the connection. Similarly, this node is connected to this node via this connection. So every node is connected to every other node in the next layer. So this is called layer 1, this is called layer 2, this is called layer 3. And each layer has different naming, but each layer, a node in one layer is connected to every other node in the next layer. So look at this. This node is connected to not just with this node, but is also connected with this node, and this node. So you have a connection from this node to this node to another node, this node to this node, and this node to another node. Similarly, all the other neurons in the same layer is connected to all the other neurons in the next layer. So this is called layer 1, layer 2, layer 3. And every node is connected to every other node in the other layer. So these are called connections. So we have defined connections in the neural network too. Now, each node is not just connected, but they are also connected with some weight in the system. So, for example, this node is connected to this node with some weight. So, if the weight is 0, that means that this node is not connected with this node, right? So, because this node, when it tries to pass the value to this node, it is like x. Say this node has value some x. So, x times W11 is the value that it will pass to this node, right? If the weight is 0, then x times W11, which is equal to 0, passes 0 weight. Make sense? So even though you have all the connections there, if the weight becomes 0, that means that that connection is not active. Make sense? But in general, a neural network that you define will have all the connections there, and while learning, if some of the weights becomes zero, that's fair. let them become 0. But it can become not just become 0, but it can become 1, minus 1, very small value, so a sufficiently large value. It can become any other, it can take any values there. So there is no restriction on what these weights can take. So these are the weights of the connections. So the connections that you have made, they are called the weights of the connection, weights of the network. So this node is connected to this node with a weight of W12. This 1 represents the layer 1, which is connected to layer 2. So which is the next node 2. So 1, 2. Similarly, the other side of the network is also connected with a different weight called V11, which is like the weight is V11. So this is a layer second's first node and the layer third first node. So V11. So similarly V12. And similarly the other nodes will be, this bar would be V21. This node connection would be V22. Makes sense? So similarly, that's how this is V42. So this is the fourth node connected to the second node with a weight of V42. Similarly, this is how the weights are defined. So now you have seen nodes or neurons, that is called the circular thing, connections with a weight defined to it. So these are called weights of the network, or sometimes it's also referred as parameters of the network. So these are weights or parameters of the network that you want to learn for your particular task. Now let's define. So this part, the input to the network, is called the input layer. So the first layer that you see is generally referred as the input layer, where where the input to the system goes through. So for example, if I take an example of a human brain, when you see something through your eye, that as your input layer that goes to your brain. So similar to the notation that whenever something comes in, the X that you see, the first layer that sees the input is called the input layer. And similarly, the last layer that actually predicts some value or that actually gives you some output is called the output layer. And in between, whatever layers are there are called hidden layer, right? So you have input layer, output layer, and any number of layers. There are currently in our example there is only one hidden layer, but it can be many hidden layers too. So, but for the sake of simplicity, all the layers in between the input layer and output layer are called hidden layers. Okay. Uh, Before I move further, is the terminology okay with everyone? I'll just wait for a minute to see if this part is okay. Okay, so we have nodes, we have connections, and each connection has its own weight. We call the input to the network as input layer, output of the network as output layer, and in between the input and output layers are called hidden layers. Okay, so now let's see what are these weights and how are they connected. So now each of these inputs that you see, x1, x2, x3 are the input. So x is the vector and these are the features of the vector. So for example, x1 is one of the feature, x2 is another feature, x3 is another feature, and these are going to the input layer. And these are the weights that are connecting. So you take x1 w11, x2 w21, x3 w31, add them, which is becomes this, and then apply a non-linear function f, right? And that's what this neuron does. It sums all these values and applies a function f on it.
Make sense? So this was the non-linear neuron that you learned before. Remember the non-linear neuron that we saw before? So this is the nonlinear function f times summation of all the sum of wi lambda I xi. This is the same thing. That each neuron that you see here is a nonlinear function now. Similarly, the next neuron would be w x1 w12 x2 w21 x3 sorry w22 x3 w32, and you sum them and apply a nonlinear function f. So this will be the value of this neuron. Okay, so all these neurons will output a a function sum of all the weighted combination of x's, and that will be the value of this neuron h1. This will be the value of h2. Why h? H is because it's called hidden layer, so h is just a representation for this neuron. So it will output h1, this will output h2, this will output h3, this will output h4. And similarly, when you actually bring all the do the same thing, because this neuron also does the same thing, that the weighted combination of all these neurons, and apply a nonlinear function f. So y1 will become h1 times v11 plus h2 times v21 h3 times v31 h4 times v41. Sum them and apply a nonlinear function to get y1. Okay, so all these neurons are weighted sum of the hidden layer and a nonlinear function f. So this is how the simple nonlinear function is now extended to a neural network based architecture. As you can see that since there are multiple nonlinear functions applied here now, so this network can represent even a much complicated functions now. It has the property to represent even more complicated representation than the simple nonlinear function representation. Okay, so these neurons that you see, the function f is generally referred as an activation function. So there are multiple choices of activation function, but we will look into the popular choices. So this is called tan h. So tan h function is like tan inverse of x. So tan h function, sigmoid function. So we have a sigmoid function. This is 1 by 1 plus e to the power minus x. As you can see, sigmoid function is always positive. Tan h functions lies between -1 to 1. Okay, so there you go. So this is your tan h function. ReLU is a very simple function. For negative values, it becomes all 0, and for only for positive values, it is just simply the same value. So y equals to x for positive value, and for negative values, it is all 0. Sigmoid also lies between 0 to 1. As you can see, the maximum value would be, if you put x equals to infinity, it becomes 1. E power minus infinity becomes 0. 1 by 1 is 1. So the values lies between 0 to 1. So if you put minus infinity, e power infinity becomes infinity. So 1 by infinity is 0. So there you go. So negative infinity goes to 0 and positive infinity goes to 1. So it lies between 0 to 1. Tan h lies between -1 to 1, and ReLU lies between 0 to infinity. So y equals to x, right? So infinity, x equals to infinity, so ReLU infinity is infinity, and the minimum value is 0. So these are some of the popular choices of activation function, where you have one activation function is called tan h, another is sigmoid, and another one is ReLU. So these are some of the choices of your activation functions. Notice that in each of the neurons that you have seen, currently we have applied f, but it is not restricted that you have to apply only one kind of activation. You can apply sigmoid here, tan h here, ReLU here, or some say any other. Say for example x square itself, like f equals to f is like x square. So you simply square the values. So you can apply any different kind of functions here. So it is not restricted that you have to apply the same function in all throughout the neurons, all throughout your layers. So it depends on your decision choice or design choice. You can choose any function f, And these are some of the popular choices of activation function f. So let me just wait here to see, at least people are able to see that how the nonlinear function, nonlinear model and neural networks are just the extension of the nonlinear models now. I'll just wait for a minute to see if everyone is able to follow this part. Is everyone able to follow? Do you have any doubt or as such? Anyone, anything on chat? Okay. So so everyone is able to follow, right? Okay. So let's move further. So these are some of the popular choices of your activation function, the function f. Now let's make it more deep. So now you can see that you can add even more number of hidden layers. So this is your input layer, this is your output layer, but there was only one hidden layer. Now you can make multiple hidden layers. You can add more layers, more hidden layers, and make it even more deep. And that's what we refer as deep neural network. Initially, there was only one hidden layer. Now you have multiple hidden layers, and you made it even more deeper. So each neuron is this complicated, is the nonlinear function that has learned through the previous layer. And by adding multiple such nonlinear functions, you have made your network sufficiently complex that it can represent any complex representation, right? Since it has the proper, it can, these neurons are sufficiently complex now, they can represent any even more complex functions, even more complex representations. And that's how they are defined. That's why they are called deep neural network, because now the network have become sufficiently deep. But why do we need such a deep layer? Consider that each, if we say each layer is called a processing step, having such multiple processing steps allows you to learn even more complex functions. And the deep network can implement not very complex functions. For example, if you want to learn a sorting of input values, so if you want to learn how to do sorting of these input values, say for example x1, x2, x3, x4, x5 is there, and you want to output what is the say middle value. So it can actually just simply output the middle value itself, which is very difficult for a linear model to do so. Or say if you have similar number of network as the, so input network has 1, 2, 3, 4, 5. Say output also has 5 networks. If you pass all the input features x1, x2, x3, x4, x5, it can output the sorted values too. If the network size, output network size is also 5, it can output the sorting of all these features according to the weight of the network. So sorting is a very difficult algorithm, even for a linear network. It can, but deep neural network can do such a thing very easily. Okay, so this is how sorting or finding a middle value, finding the maximum value. Maximum value cannot be found through a linear network, because you cannot simply design a linear net weight which can actually output the maximum value or the minimum value or the middle value. So you can see the deep neural network can actually output those network if you make your network deep enough. Okay, so this is why we actually use this deep neural network. So assuming this part is okay, I will request students to stop me if they are not able to follow. Okay, it would be interesting if others, if they are, if they have doubts, they can ask those questions or raise these questions there itself. Okay, so let's look into what does it mean to do a forward pass in the neural network. How do we calculate anything through the network? Say, for example, an image of car is given to you, and say the image of the car has these feature. X1 feature is 1. Say, for example, it has 4 wheels. Okay, 1. It has a handle. The feature is 0. It doesn't have a handle. It has a upper body head. Yes, true. So 1. So they say these are the three features there of a car. So 101 is the input vector of that goes into the neural network input. So 101 goes into, and say the initial weights of these weights are zero point 0.2, these are zero point 0.5. Similarly, all the weights are defined 0.25, and similarly the other V1 weights are also defined. And after computation, it outputs Y1 and it outputs Y2. So you take these network 101 goes through the network and outputs certain value. So for example, let's do this thing. So this network, all the neurons over here, the input layer, since there are no activation function here, it simply the neuron becomes 1, this becomes 0, this becomes 1. Now it goes to the hidden layer. So how does it go? X1 1 times zero point 0.2, 0 times this value, this weight, 1 times this weight, and you apply some activation function. In this case, we have applied a sigmoid activation function, which just maps values between 0 and 1. And you get the value of this neuron, which is 0.668. So this value becomes 0.668, this value becomes 0.912, this value becomes 0.102, this value becomes 0.471. In all these layers, we have applied uh, all these neurons, we have applied a sigmoid activation function. The nonlinear function is a sigmoid activation function. Now, once you have these values 0.668 for this, 0.912, 0.102, 0.471 for these neurons, now we pass it to through the other next layer. So we actually take this 0.668 times 0.1 plus 0.668 times 0. Not 0.668 times 0.1, 0.912 times this weight, 0.102 times this weight, 0.417 times this weight, and apply a sigmoid network, and we get 0.812. Did you see? You are able to. Everyone is able to follow that these neurons, the output of these hidden layer is now used a weighted combination times sigmoid layer to output the next layer output and next node output. Okay, that's how you get 0.812. Again, you have applied a sigmoid network. It's not sigmoid here. It's softmax here. It's a different, altogether different activation, which we have not covered yet. But it's also a very popular activation function. You just simply apply a softmax after this. So just once you calculate this, this is the value that you get after applying a softmax activation function. So you will learn all these things in the tutorial, why softmax is used, why not sigmoid again. But assume that there is another activation function called softmax that you applied here. And that's how you do a forward path. You take the input, you pass it through the network one at a time, and that's how you get the values. I will wait here to see if there are any doubts, because after this we will now move into how do we do it fast. Or if the basics are clear, then we can move into how do we do it through other ways, alternative ways. Okay, assuming this is okay. So we can convert each of these weight matrices into a bigger, all these weights that you see as scalar weights into a weight matrix. So what does it mean is, they say, for example, the input is I1, and corresponding H1 is W11. So I1 corresponding weight is W11. I1 corresponding H2 is W12. So W12. I1 corresponding H3 weight is W13. I1 corresponding H4 weight is W14. And similarly for I2 and I3, so for these are the values of this neuron, which is actually I1 is equals to x1 because there are no activation function, nothing is there. So I1 is equals to x1, I2 is equals to x2, I3 is equals to x3. But for generalizability, let's write I1, I2, I3 and H1, H2, H4 are the weights, corresponding weights of this neuron that connects these weights, connects these neurons. So these are the weights for this connections. Similarly, for the next connections, we have a weights V11, V12, and V41. So H1 with O1 connects with V11, H1 with O2 connects with V12, and similarly for H2, it connects with V21, and H2 with O2, V22, H4 with O1, V41, H4 with O2, V42. And that's how you have a V matrix, right? We can write this W matrix and V matrix now, right? Now, if you look at our first H1 calculation, it's like we take x101 and we multiply with this vector. You see, H1 x1 times W11, this part, 0 times this part, right? Because H1 will go, but you are trying to calculate the neuron 1's value, right? So 0 times W21, 1 times W31, right? You can take this vector and multiply with this vector, and that's how you get 0.668. Similarly, if you want to calculate the and then apply the sigmoid function over this. If you want to calculate the neuron value of neuron H2, you take this vector and multiply with the H2 vector in the W matrix, and that's how you get 0.912. So if you see what you are doing is, it's like if you want to calculate this vector, you first have to do, this is X transpose because X is a vector, 101 vector. So you did a X transpose and you multiplied with this W vector, right? This times this times this times this times H4 to get the H4 value, and you X transpose times W, and then you applied a sigmoid to get H transpose, right? So this was a H transpose vector. Okay, so you get this value, X transpose W sigmoid is a H transpose vector. So you have this vector. So you see that it has become very simple. Now you just need to know the weight of this network. The weight of the weight of this network is simply W. So X transpose times W and apply sigmoid, you get the entire vector directly. You don't have to do manually calculating every point. You just simply do a matrix multiplication. Okay. I'll wait here for a minute to see if there are any doubts here. If everyone is able to see that this is simply a sigmoid of X transpose W to calculate the weights of the hidden network, hidden layer. Okay, if there are no further doubts, let's move further then. Similarly, we can use this H transpose, this vector, times v to calculate y transpose, right? You can take this vector and multiply with O1 vector to calculate the output for y1. You take this H transpose and multiply with O2 vector to calculate get the value of y2, right? And that's how you get y transpose. This is H transpose v times the sigmoid network, and that's how you get these values. That's it. So now the entire function looks like this. So you have x transpose w sigmoid times v of the sigmoid to get the y value. So you can see that it's a complicated function. You have a nonlinear function here and then another nonlinear function here. So y has become a sufficiently nonlinear function with a much better representative power than the simple nonlinear function. Okay, I will just wait to see if everyone is able to see that this equation they are able to see. Okay, if there is no further doubt, so let's move ahead then. Okay, so now how do we learn the weights of the neural network? We have seen how to do forward pass. We have understood what are the terminologies of neural network. So now whenever you see NN, it means neural network. So how do we learn the weights of this network? So these W's and V, how do we learn this? So let's consider an example. So let's say for example, we pass this car example 101 and pass it through the network and say y1 is the probability that the prediction is bike and y2 is the probability that it is a car. So it predicts the value of 0.812 and the car probability with 0.151. And you can see that it is definitely not a bike. The truth is that the bike probability is 0 and the car probability is 1. So there is definitely an error in your prediction, right? So this is what we call error. So it has predicted that it is a car, it's a bike with probability 0.812, and it has predicted it's a car with 0.15. So it's like this is definitely not correct. You want the car probability to be high and the bike probability to be low. So you want to update the network's weight W and V such that the car probability becomes higher when it sees a car and the bike probability becomes lower. The truth is the bike is probability 0 and the car is probability 1. So we can see that there is an error between these two. So we say that this part is y vector. Y vector is 0.812 and 0.151. This is y vector, so y bar. And 01 is the truth value. So y bar bar. So there is this hat, this is bar there, y tilde is the truth value. And if you do a mean squared error of that, is the error in the error of the model. So this is what the error in the prediction, right? And we define this error, also it is known as the loss function. So this is defined as mean squared error. So what we are using is a squared error. And if you divide it by the total number of examples, it's called a mean squared error. So what we are using here is a squared error to calculate the error of the system, error of the network. Okay. So you have the input and the label, the truth value, and you calculate the error between them. And you can define an error as a mean squared error, which is also known as loss function. So there are different functions. We are here using a mean squared error loss function. Okay. So how do we how do we minimize? You want this error to be minimum. You want to learn the weights of the network such that the error is low. Or when will the error become zero? When the bike prediction becomes zero and the car prediction becomes one, then the error will be zero. But in general, it may not ever reach a zero error. But what you want is the error should be as low as possible. So how do we minimize this loss function? Assume that this curve that you see here, this U-shaped curve, say this is your loss function, and lambda is the weight of the network, and you want to find a lambda such that the error is minimum. So you can see that this is the optimal lambda. This is the point where you want to go. You are currently at some lambda here, and you want to reach this optimal lambda. This is the goal that you want to reach. So how do you do that? You first calculate the gradient of the error function at this point. So you calculate this gradient, right? This is the gradient of this function, a tangent value. And notice that the gradient is positive. See, tan of this theta is positive, right? Even the gradient at this point is positive. And the minimum value lies in the negative direction. So this is positive. So you from this value point, you have to go in the negative direction of the gradient. The gradient is positive and you need to go in the negative direction, the backward direction. If you go in the positive direction, you will go forward to the current lambda, and the optimal lambda is behind your current lambda. So you need to go in the negative direction of the gradient, right? And we update because the minimum value is in the negative direction of the gradient. And we update the new lambda, say by going a small value, you go a very delta direction in the negative gradient direction. So lambda new is equals to lambda current minus negative direction of the gradient, eta times the gradient. Eta is a very small value, so it says 0.001. So from here, you move to this particular point. Again, if you move from you calculate the gradient and the gradient is still positive, you move a very delta step, you go here. You go a delta step again, you go here, and again you go to the optimal value. So if you continuously move in the negative direction of the gradient, you will reach your optimal value, and the gradient at the minimum value becomes zero. You see? Now, even if you update at the optimal value, if you try updating your network, it will simply stay at the same location because the gradient is simply zero. So optimal lambda is becomes the current lambda because the gradient at that point becomes zero. Okay. So if you continuously go in the negative direction of the gradient with very small eta, you will reach your optimal value. I'll wait here to see if everyone is able to follow the gradient descent algorithm. Okay, if there are no other doubts. So now we know how to calculate how to find a minimum weight. Say for example, if the error depends only on this lambda parameters, we are able to find how to optimize for this lambda. Similarly, we have defined our error in our network as the mean squared error. So we just simply have to calculate the error with respect to the weight W. So say initially you are at weight Wt, you calculate the gradient, which is d error by dw, t, you calculate the gradient, and you just have to move in the negative direction of the gradient. So your new updated weight Wt plus 1 at the new time step would be Wt minus eta times the gradient with respect to the weight. Similarly, for V weight, you just have to similarly calculate the gradient with respect to V, right? And that's how you update your network. And at optimal point, this gradient will become 0. Then Wt plus 1 is equals to Vt plus 1 is equals to Vt. That means your V has reached your optimal weight, and hence your gradient has become 0, right? So your at minimum optimal error, the gradient will become 0, and hence your weight will never change, right? And that's how you train your neural network. You train your neural network such that the weights become such that the error becomes minimum, and that's how you train your neural network. That's the entire idea of how do you train your neural network, how do you update your weights such that the error becomes minimum. Now there are some computational things that we need to look into. So rather than using the entire data set, so you have a data set of uh, X and the corresponding label Y. Since the data set can be a very large data set, so we don't use the full data set to calculate the error. We use a small subset of the data set, which we call it batch. We use this small subset of data set to calculate the loss and update the weight. And we do this small update of batch multiple times until it converges. We only use this small subset of dataset. Mostly it is done for the speed and computational reason, because you do not have such large RAM or GPU memory such that it can hold the entire data in the memory. So you either it is done mostly due to speed and computational resources reason. That's how we use small batch, and it has been found that even with using a small batch of data, the network learns well and it is stable. So this is the small caveat that we use, and we will see this thing more properly in our tutorial tomorrow. So that's all I have for today. So we have completed neural network, the terminologies of the neural network, how do we define what is forward pass in the neural network, how is error defined, how do we update our weight such that the error is minimized, and a computational reason, how do we use batch in the dataset such that we are not we are not exceeding the memory limits of our device. So yeah, that's all I have for today. If there are any doubts, please you can ask them. Are there any doubts? Okay, I don't see anything. So if you have any doubt, you can ask now. Okay, there seems. Okay, if there are no doubts, let me then share the slides first. So if someone can confirm if they can see the slides. Are you able to see the slides?
Yes, sir.
Okay, thank you again. So if you have any doubt, please let me know, or else we can end the lecture. And tomorrow we will see a tutorial on neural network. Okay, it seems like no doubt. Please go through the slides once, and we'll do tutorial tomorrow. And see you tomorrow in the next lecture. Then, thank you. Then, so we can end the lecture now.